Hey everyone, and welcome to This Explainer. Today, we are unpacking a really foundational challenge in modern artificial intelligence, drawing from an excellent primer over at Amman's AI journal. We're looking at factuality in large language models, or essentially, how we actually engineer the truth. Let's dig right into this, because this isn't just about making AI sound smarter anymore. It's about figuring out how to make it systemically reliable from the ground up.
So let's kick things off with a pretty massive question. Can an AI truly know the truth? Think about it. As we start relying on these systems for, medical summaries, legal drafting, or critical financial analysis, the real-world stakes become incredibly high. A smooth, confident, grammatically perfect answer, that just isn't enough anymore. We need absolute certainty that the information the AI gives us is anchored in actual reality.
Okay, let's dive into this. To really get a grip on factuality, we first have to separate it from a buzzword we hear literally all the time: hallucination. Hallucination is essentially about internal inconsistency. It's when the model makes up claims that sound coherent but are totally baseless. Factuality, on the other hand, is entirely about external, verifiable truth. Honestly, it doesn't matter if the AI's logic flows beautifully. If it doesn't align with credible real-world evidence, it is just not factual.
Here is our roadmap for today. We'll start by defining AI factuality. Then we'll map out the taxonomy of truth. From there, we'll look at grading the AI, how engineers are actually fixing the machine, and finally, the future of truth.
All right, Part 1. Defining AI factuality.
The absolute most important thing to grasp here is that measuring factuality is completely distinct from measuring fluency or grammar. An AI can produce award-winning, beautiful prose that is entirely factually bankrupt. Factuality isn't some qualitative vibe, right? It's a formal, quantifiable mathematical function, represented here as f of xy. In plain terms, this is the exact proportion of an AI's claims that are actually supported by ground truth evidence. We are demanding a hard, concrete measurement of truth.
Moving right along to Section 2, the taxonomy of truth.
You see, truth isn't just one single monolithic concept in the AI world. We really have to categorize it. On one hand, we have intrinsic factuality. Think of this like a closed book exam. The AI relies entirely on the world knowledge it memorized within its parameters during training. On the other hand, we have extrinsic faithfulness, which is basically an open book exam. This is where you hand the AI a specific document, like, say, a 50-page earnings report, and you measure how faithfully it sticks strictly to that text without inventing any outside info.
Building closely on that, we have this idea of groundedness, which is a wildly critical concept for systems using Retrieval-Augmented Generation, or RAG. Groundedness demands two very distinct things. First, the evidence the system retrieves must be both highly relevant and sufficient to actually answer the prompt. Second, the AI's generated output must be perfectly faithful to that retrieved text. The AI explicitly has to show its work, proving beyond a doubt its answer is anchored in the high-quality data it just pulled.
Now, what's really interesting about this slide is how we actually measure this in long-form text, which has historically been super difficult. Frameworks like Google's SAFE break the process down into this incredibly simple, logical recipe. Step 1, extract atomic claims. You're chopping a sprawling essay into individual, verifiable statements. Step 2, search for external evidence for every single one of those claims. And Step 3, verify entailment. Basically, checking if the retrieved evidence logically proves the claim.
But of course, things still go wrong. Here's a quick, rapid-fire look at how AI fails in some pretty predictable ways. You have entity errors, like an AI claiming the Eiffel Tower is in Berlin. Relational errors, saying Einstein studied under Bohr, when actually they were peers. Compositional errors, which is incorrectly combining true facts into a false conclusion, like Newton invented calculus, therefore he won a Nobel Prize. I mean, he's about 2 centuries late for that. And then, perhaps the most dangerous, entirely fabricated citations, where the AI literally hallucinates a fake research paper just to back itself up.
Okay, Section 3, grading the AI.
Since having humans manually fact-check every single AI generation is incredibly slow and, frankly, way too expensive, researchers use robust, automated diagnostics to test models at scale. And as we can see across these domains, there's no one-size-fits-all metric. If you're building a RAG pipeline, you use RAGAS to check retrieved documents. For open-world knowledge, you'd use SAFE. FactScore uses another LLM as a judge, and QA FactDevel is designed perfectly for testing document summarization. It's all about picking the right tool for the job.
And this brilliantly illustrates how the final output of those grading frameworks works. It doesn't just give you a simple pass or fail, you get a quantified, aggregated breakdown. Imagine processing a really complex AI-generated report and getting this diagnostic back. 75% of the atomic claims are fully supported by evidence. 15% are directly contradicted, meaning it identified exact hallucinations, and 10% are unverifiable. It completely takes the mystery out of the AI's performance.
Which brings us to Section 4, Fixing the Machine.
So now that engineers have these detailed diagnostic scores, how do they actually get in there and code truth into the architecture? Well, there are 3 exact intervention points. Phase 1 is training time. This is curating ultra-high-quality data before the model even learns its basic parameters. Phase 2 is inference time, adding live retrieval systems right as the AI generates its answer. And Phase 3 is post-hoc, which is giving the model the ability to self-reflect, critique its own output, and issue corrections after the draft is completely done.
Let's zoom in on a really cutting-edge Phase 2 strategy, verifier-in-the-loop decoding. Guys, it is amazing how this works. As the AI generates its response, a secondary verifier model checks the facts mid-generation. If the AI predicts a word that contradicts the retrieved evidence, the system literally blocks it before the sentence is even finished. It acts as a dynamic, real-time guardrail, keeping the AI grounded. No more waiting until the end to find out it made a mistake.
Finally, Section 5, the future of truth.
So how does all this integrate into the enterprise apps we rely on every single day? In the real world, factuality isn't just a one-time test passed in a laboratory. Real-world knowledge constantly evolves, right? CEOs change, companies merge, new discoveries are made. Because of that, production systems require continuous factual monitoring. We are looking at real-time fact logging and actively detecting what's called factual drift as the model's static memory becomes outdated. It requires a continuous, living loop of auditing and human oversight.
So, the crucial point is really captured in this shift. The field is now transitioning from merely detecting hallucinations to engineering actual truth maintenance systems. We are moving entirely past the era of treating AI hallucinations as some spooky, unavoidable mystery. And we're starting to treat factuality exactly as what it is, a solvable, rigorous systems engineering problem.
Which leaves us with one final, pretty provocative question. As these truth maintenance systems scale up, and as AI increasingly becomes our primary interface with all human information, who ultimately gets to define the ground truth that these models verify against? It's an incredible technical challenge for sure, but maybe more importantly, it's a profound philosophical one. Thank you so much for joining me on this explainer. Keep learning, keep asking those big questions, and I'll see you next time.